Welcome to this explainer. Today, we're going to decode the microscopic optical physics of a hidden technology. It's a tech that plays a massive, yet completely silent role in keeping our everyday infrastructures safe. Honestly, if you've ever wondered how engineers actually monitor the health of the physical world around us, well, you're definitely in the right place. Let's get right into it.
But before we zoom way down into the microscopic world, we really need to start with a massive, real-world problem. Think about it. How do we actually know when the huge structures we rely on every single day, like those concrete bridges we drive over or the massive skyscrapers we work in, are under dangerous strain? I mean, we need to know for sure before they fail, right? They can't exactly speak to us. We need a way to literally see the invisible forces acting upon them.
So, that brings us to Section 1, defining Fibre Bragg Gratings. Let's unpack exactly what a Bragg grating is. Okay, so a Fibre Bragg grating, or FBG for short, is defined as an optical fiber sensor containing periodic refractive index variations that reflect a specific wavelength of light. Now, I know that sounds like a serious mouthful of physics jargon, but stick with me. At its absolute core, an FBG is essentially just a customized section of an ordinary optical fiber. It's been cleverly modified to serve as a highly specialized sensor, so we can precisely measure things like strain and temperature. To really wrap your head around this, I want you to imagine this internal grating acting like a microscopic smart mirror. Just picture this tiny mirror trapped inside a hair-thin glass wire. But it's not a normal mirror. No, it's highly selective. It only catches one very specific color, or wavelength, of light, and it happily lets all the other colors pass right through it, exactly as if nothing was even there. It's kind of mind-blowing when you think about the scale of it. Moving on to Section 2, the inner structure revealed. Let's take a look at the actual anatomy of an FBG sensor. If we zoom all the way down into the fiber, we basically see just three crucial physical layers. First up, you have the optical fiber core, right in the center. Think of this as the main highway for the light. Second, you've got those periodic refractive index variations we just talked about. These are the actual gratings, meticulously etched right there within the core. And finally, the third layer, surrounding the whole thing, is the protective cladding to keep all that light perfectly contained. It's truly a masterpiece of minimalist engineering. All right, Section 3, how the working principle operates. Let's see how this physical structure actually works in practice. Let's follow the chronological journey of a single beam of light. Step 1, a broadband light source, which remember contains a whole bunch of different wavelengths, fires directly into the fiber. Step 2, when that light hits the grating, our tiny microscopic smart mirror springs into action. It reflects just a single specific wavelength backward. We call this the Bragg Wavelength. And step 3, the rest of the light just continues completely uninterrupted right down the line.
Now, here is the absolute crucial point in the physics. Pay attention to this part. When the optical fiber gets squeezed or stretched or even heated up by the outside world, the actual physical spacing of that tiny grating changes. And when that spacing changes, that specific reflected Bragg wavelength actually shifts. So a new physical spacing means a slightly different color of light bounces back.
So you might be sitting there wondering, okay, why does this specific wavelength shift even matter to me? Well, here is your main takeaway. This microscopic optical shift is exactly how the sensor talks to us. By precisely measuring that shift, engineers instantly know the exact strain or temperature being applied to the fiber. It tells them with absolute certainty and in real time if the bridge you're currently driving over is experiencing dangerous physical stress. Pretty incredible, right?
Which brings us nicely to Section 4, the key advantages. Here's exactly why FBG sensors excel.
This tiny tech boasts massive advantages over those traditional clunky electronic sensors we're used to. For one, it provides incredibly high sensitivity and accuracy. Plus, because it relies entirely on light and glass, rather than electricity and copper wire, it is completely immune to electromagnetic interference. Zero static. And on top of all that, it's so small and lightweight, it adds practically zero bulk to whatever structure it's measuring.
And these advanced capabilities are exactly what makes FBGs so highly scalable. You can use these fibers for remote sensing over vast distances without losing the signal at all. But here's the best part. You can actually string multiple distinct FBG sensors along a single continuous optical fiber. You literally just tune each grating to reflect a different starting wavelength. Boom! Suddenly you have this massive, interconnected nervous system of sensors, all reporting back through one single hair-thin wire. Let's transition to Section 5, Real-World FBG Applications.
Let's see where this technology actually lives out in the wild.
When you get right down to it, FBG applications are rooted in two core capabilities: pinpoint temperature measurement and exact strain measurement. But here's the thing. Everywhere in the world that highly accurate data on those two specific factors is a literal life or death requirement, well, FBG technology is very likely working silently behind the scenes. This directly translates into some incredibly vital industrial use cases. We're talking about constantly monitoring the structural health of massive suspension bridges and towering skyscrapers to prevent catastrophic collapses. We're talking about embedding these tiny fibers directly into the composite materials of aerospace vehicles and aircraft wings, keeping everyone safe mid-flight by measuring the stress on the wings in real time. And, of course, it's heavily utilized to regulate super intense industrial process controls, where traditional electronic sensors would literally just melt or fail. It leaves us with a truly fascinating thought to end our explainer on today. Think about it. If customized microscopic strands of glass can successfully monitor the immense physical strain of massive airplanes and giant suspension bridges, what other invisible structures and hidden forces in our world will we soon be able to see and monitor? As this microscopic optical technology continues to scale, the possibilities for making our world safer are practically endless. Thank you so much for joining me, and keep questioning the invisible mechanics of the world around you.